The last thing that I want to discuss in terms of ring homomorphisms is not entirely related to ring homomorphisms, but is covered in this chapter of Galilean. And this is the definition of a quotient field. So in general, let's talk about the idea behind quotient fields first. In general, an integral domain is not a field. And our perfect example of this is the integers. This is an integral domain, but this is not a field. However, we know that the ring of integers is contained inside many fields. It's contained inside the rational numbers, the real numbers, the complex numbers, and more than that even. And so the question is, if we start with an integral domain, all right, it's not a field. But is there always a field that contains it? Can we take our integral domain and put it inside some sort of field the way that we can do with the integers? And if we can, is there a smallest such field? Is it the case that we can find a minimal such field, and will that thing be unique? As it turns out, I'm not going to make you wait very long for the answer. The answer is yes. There is a unique smallest field containing a given integral domain D, and what we do is we call this the quotient field of the domain D, or the field of fractions of the domain D. I think that I prefer the phrase field of fractions of D. I think it's slightly more descriptive, but I know that Galilean, for instance, uses a quotient field. And here's the idea. What we're going to do is we're going to build a field that contains our given integral domain D. Now, the idea behind this is there's a formal way that we have to go about it, which is what I'm going to outline in these slides and what I'm going to do. But let me give you the way that you should be thinking about this. Think about the integers. Think about how they're an integral domain, and we need to find multiplicative inverses for all of the numbers that we have in our integral domain. So we start out with something like 4, and we're looking for a multiplicative inverse for it. So what we could do is we could just say, start with the domain, the integers, and then start adding on all of the inverses that we need. Start adding on things like 1/4, 1/2, 1/3, and so on and so forth. However, we also need this type of a thing to be closed if we're going to have any sort of possibility of things like this happening, which means we need to be able to add these fractions together. And so when we do, we might end up getting something that does not have a 1 in the numerator. So the idea is, if we would have started with the integers, we would have ended up with the rational numbers when we do this process, which is something we'll see. But what we want to do is, if we change from the integers to just an arbitrary integral domain, what we want to do is kind of look at just the field of fractions of this thing. We want to look at all things of the form one element of the integral domain divided by another element of the integral domain, and we want to say that that's the field we're looking for. The problem that we run into is that we have this notion of equivalent fractions. Going back to the integers, we have this problem. 1/2 and 2/4 are kind of considered the same, but with that first definition that I gave you, they wouldn't necessarily be thought of as the same. So what we're going to have to do is this roundabout method that kind of talks about, which kind of hints at cross multiplication for checking to see if fractions happen to be equivalent. And so that's the catch, is that we can't just look at things of the form one element of the integral domain divided by the other element of the integral domain and end up with a field. So we're going to have some things that we really want to end up thinking about as the same. So to get around this, what we do to create this field of fractions is we start out with a set. It's just a set, so I'm going to name it S. It's going to be the set of ordered pairs A comma B, where we require that A and B be elements of the domain D, the integral domain, and we're going to require that the B be non-zero. So we're thinking of the A as sort of a numerator of a fraction and the B as sort of the denominator here. But what we're going to do is we're going to define two different elements of this set S to be considered similar or equivalent. If it happens to be the case, if I have A, B, and C, D, I'm going to consider them equivalent if A times D is equal to B times C. So again, this should remind you a little bit of cross multiplication that's going on in the integers and the rational numbers. And it's an exercise, one that I think you ought to do, to show that the thing that I've defined, this tilde, is actually an equivalence relation on the set S. So remembering that an equivalence relation is something that's reflexive and symmetric and transitive, I think it's a good exercise to work through, showing that those properties hold of the equivalence relation we've defined here. What we're going to do is, from this set S, we're going to build something called F, which will turn out to be a field, F for field, to be a set of equivalence classes of F. So that's equivalence classes of S, I'm sorry. So if A and B, A comma B is an element of the set S, what we're going to do is write A over B for the equivalence class of F that contains this ordered pair A comma B. Now, we've defined a set. We have a set of equivalence classes. We've called it F. If we want it to be a field, we need to talk about how do we add two elements together, and we need to talk about how do we multiply two things together. So let's say that A over B and C over D are elements of this set F, so they're equivalence classes of these ordered pairs. We're going to say that we add them together by saying A over B plus C over D is equal to the class that contains the number AD plus BC over BD. So finding that, so just like it is with rational numbers, finding a common denominator to be the product of the denominators, and replacing fractions for equivalent fractions and adding across. And then we're going to define multiplication the way we're used to it for rational numbers as well, where we just multiply across the tops and the bottoms. A over B times C over D is AC over BD. And again, replacing with equivalent fractions if necessary. The claim is that this set F that we've defined, this set of equivalence classes, is actually a field. Now, to prove that something is a field, you've got a lot of things to check. You've got to check that it's a group, that the group operation is commutative, you've got to check that there's a multiplication, you've got to check that you have a unity, you've got to check everything as a multiplicative inverse. Associative properties hold, distributive properties hold, lots of things to check. This is really tedious and I think would be a waste of our time and would bore you, quite frankly. But one thing that we're going to do is we're going to check that multiplication is well defined. So what I mean is, I've taken A over B and C over D to be elements of F, and these are members of equivalence classes. What I've done then is I've picked a representative from each equivalence class, the numbers A and B, one ordered pair A and B, one ordered pair C and D. I've done that multiplication and I've gotten AC over BD, and I've said that should represent everything inside the equivalence class. But I started with something really specific. Why should A over B be considered more special than perhaps a different element of the same equivalence class? Why should I let A over B speak for the whole equivalence class instead of something like A primed over B primed? So that's what we're going to check, because this is something that we forget to check very frequently. So what we're going to do is, kind of as I described, we're going to show that if A comma B is an ordered pair, and A primed B primed is an ordered pair, and they happen to belong to the same equivalence class inside of F, and similarly for C over D, then the answer that we get by taking A over B and multiplying by C over D is the same answer we would have gotten if we would have instead picked A primed over B primed and C primed over D primed. So sure, we let A over B and C over D be special representatives of their equivalence class, but we would have gotten the same answer if we chose differently, and so it doesn't matter that we let them be special. That's the point of showing that this is well defined. All right. So by definition, when we look at A over B times C over D, we've defined that multiplication to be AC over BD. And similarly, if we looked at A primed over B primed times, should say C primed over D primed, what we would get is A primed C primed over B primed D primed. Now what we have to check is that those two different answers that we get, A over C, AC over BD, and A prime C primed over B prime D primed, we have to check that they're really equivalent. And what it means for them to be equivalent, the definition of our equivalence relation, was that the AC multiplied by B prime D prime needs to be equal to the A prime C primed multiplied by the BD. Again, remembering that if you're having a hard time remembering what that equivalence relation was, it's like cross multiplication. Now, we have to use the fact that A over B is in the same equivalence class as A primed over B primed, which means, again with our cross multiplication, that AB primed is equal to A prime B. So when we make that substitution, we can start with a c b prime d prime, and we'll just swap out the a b primed for a prime b. Similarly, the c over d was in the same equivalence class as c primed over d primed, so we have that c d primed is equal to c prime d. Now when we make this second substitution on top of the first, what we end up with is that a primed c b d primed is equal to a primed c primed b d, and putting that all together with the transitivity of equality, we have that ac b prime d primed is equal to a prime c prime b d. And so what that shows, again, is that this multiplication is really well defined, which is one of the sneaky things that we would have subtly had to check if we were checking all of the number in the teens things that we would have to check to show that F is a field. The last thing is, so I've talked about, I've waved my hands at it because it is quite an annoying thing to work through in full detail, but I've talked about, here's the process, start with a domain, let's build this field of fractions for the integral domain D. The question is, what we really wanted all along was for our domain to be contained inside of the field. Strictly speaking, our domain is not contained inside of the field. On the one hand, I was dealing with elements of an integral domain, and then what I did is I made ordered pairs of them and put an equivalence class on those ordered pairs. So we're really talking about comparing apples to oranges and oranges to bananas here. So it's not true that apples are contained in the subset of bananas, but what is true is that I can find a collection of bananas that really are the same as the collection of apples that I started with. So what that means in terms of abstract algebra speak is that the integral domain D isn't really contained in F, but it's isomorphically embedded inside of F. That is, we can find a copy of D that's sitting inside this new thing F that we've defined. So the way we're going to show that is we're going to use ring homomorphisms. So we're going to take a map phi that goes from the domain to this new set F that we've defined by taking an element A and mapping it to A over 1. So that would be like with the integers, taking the integer 2 and saying, yes, strictly speaking, the integer 2 is not an equivalence class of the things related to 2, like 4 over 2 or 6 over 3. But we can take 2 and we can map it to 2 over 1, and then it is, in essence, sitting inside these rational numbers. So what we want to do is we want to check that phi is a ring isomorphism. So we need to check that it's a ring homomorphism, and then we need to check that it's going to be injective. And then what will happen is that D will be isomorphic to its image, phi of D. On this side, let's check that what we really have is a ring homomorphism. So let's show that phi of A plus B is equal to phi of A plus phi of B. By definition, phi of A plus B is equal to the quantity A plus B divided by 1. And here's the magic trick that we need. What this is equal to is we need to take 1, which is this unity, and we need to rewrite it as 1 times 1. And when we do that, we can then split up our fraction according to the way that we've defined addition inside of F to say that the quantity A plus B over 1 times 1, I can take one copy of the 1 and give it to A, and the other copy of the 1 and give it to B. And this is equal to, according to our definition of multiplication and the fact that 1 is the unity, this is equal to phi of A plus phi of B. Similarly, we can do the same thing for multiplication. We need to show that phi of the quantity A times B is equal to phi of A times phi of B. And so here we're going to do the same trick. Phi of AB, by definition, is AB over 1. And this, by the same trick, I mean we want to write 1 as 1 times 1. Then we can split things up. So AB over 1 times 1 is A over 1 times B over 1. And this is precisely phi of A times phi of B. So this shows that the map phi is a ring homomorphism. What's left to show is that phi is a one-to-one map. So first let's do this according to the definition. Let's suppose that A and B are two elements of the domain and that phi of A is equal to phi of B. What this means is that A over 1 is equal to B over 1. According to the way we defined our equivalence relation, this means that A times 1 is equal to B times 1, doing this cross multiplication idea. and A times 1 is A and B times 1 is B, so we conclude that A is equal to B. This shows injectivity just according to the definition. I start with two elements and suppose that their images are equal, and what I concluded was that the two things I started with must be equal. The other thing that we could do is we could check that phi is 1 to 1 by checking that if phi of A is equal to 0 over 1, which is this additive identity in the set F, then A must have been equal to 0. That is, we can show that the kernel of this map phi, which we know is a ring homomorphism, is just the set containing 0. This is kind of a nicer way to do this problem because it really uses that property of ring homomorphisms that we've discussed earlier on. And the proof of this is very straightforward and quite simple, and I'm leaving it to you as an exercise just to help you strengthen your skills at working with properties of homomorphisms. Just to summarize this page then, we said that D and its image, right, we established this map phi, and we showed that it was a ring homomorphism, and we showed that this ring homomorphism was 1 to 1, or injective. So when we then consider phi of D, which is the image of D, we have that phi of D and D are isomorphic, and we can think of phi of D as being D, and then it's really contained inside of F. I did want to give a couple of examples just to help you better understand this concept. I hinted at this and was sort of using this as my running example as we went through these slides, but the field of fractions of the integers is the rational numbers. Something that's perhaps a little bit less easy to see, but is an example of a general phenomenon, is that if the field of fractions of z mod p is just z mod p. It's not any bigger at all, and it's just itself. What this means is because z mod p is a field, everything really has a multiplicative inverse inside of z mod p. And so the more general fact is that if you start with a field, then its field of fractions is itself. Now, another thing that's somewhat interesting and that may come up to us later is the field of fractions of the polynomial ring R adjoined X, which happens to be an integral domain. It's F. I've written F symbolically kind of in a bad way. F is polynomials little f of x over g of x, where g of x is not just the number 0. It's not true that F is actually equal to this set. F is equal to equivalence classes of things of this form. So for instance, if I had the polynomial x minus 2 over 1, this should really be equal to the polynomial x times the quantity x minus 2 over x. So those two things would be considered equivalent inside of the set F that I have listed here. But this field that talks about things basically in their reduced form, if you think of f of x and g of x having no common factors, then this definition of F is okay. And this field F is often denoted a boldface R with a round parentheses X. So instead of the square brackets, which is this adjoint notation, if you do R and then open parentheses X, what you normally mean is the field of fractions of the ring R. Now this concludes the material that we want to cover, but there were a lot of videos here, so after studying these slides, these 5 different videos, and your textbook, and perhaps doing some exercises and examples of your own, these are the things I'd really like you to take away and I'd hope you'd be able to do. The first thing that I want is all of the new definitions that we've introduced, so things like a ring homomorphism and the field of fractions, kernels, images, etc. I'd like you to really understand and know by heart the definition of these things. The second thing I'd like you to know how to do is to use the properties of ring homomorphisms and the first isomorphism theorem for rings. So we've had a couple examples of how we could apply the first isomorphism theorem for rings, and we've also had some examples in the z mod 20z maps to z mod 10z, kind of giving you examples of how to use properties of ring homomorphisms. The unity must map to the unity of the image, etc., to come up with specific ring isomorphisms from one ring to another. The third thing I'd really like you to be able to do is compare and contrast group homomorphisms and ring homomorphisms. Throughout this slide, there are maybe 2 different places at least where I talk about things that are group homomorphisms but are not ring homomorphisms. And very frequently I would talk about, oh, this property for a ring homomorphism follows because it is a group homomorphism. I'd really like you to be clear on the relationship between a group homomorphism and a ring homomorphism, and be able to come up with examples sort of in both directions. And last but not least, I'd like you to feel comfortable performing computations. If I give you a specific map, if I tell you what maps to what, I'd like you to be able to do some computations to verify if that map is a ring homomorphism, a ring isomorphism, or a ring automorphism. Now, I didn't explicitly define a ring isomorphism or a ring automorphism in writing on each of these slides, but you really ought to, at this point, be able to generalize from the fact that you know what a homomorphism, an isomorphism, and an automorphism are, and you know what a ring is. You should be able to piece together the proper definitions of those words as well.